Let's look at a typical exam question that relates to aromaticity. So you've got your compounds here and it says fill in the molecular orbital diagrams below each structure. So we each have, each of these have energy going upwards. So what we need to do is just count up the number of pi electrons or electrons in the pi system, after making sure, of course, that they're either aromatic or anti-aromatic. So we look here and we assume these to be flat to begin with, so that's not really part of it. But we need to see if we have a cyclic system, which we do in each case, and we need to see if we have an alternating system or a conjugated system, which we do in each case as well. Single, double, charge, single, double, single. So both of these are going to be conjugated as well. So they're either going to be aromatic or anti-aromatic, but neither of them would be not aromatic. So if we count up the number of pi electrons, and this one's going to come out to be 6 pi electrons. We've got 2, 4, and then 6 here. The negative charge, if we want to sort of take a closer look at it, is actually 2 electrons. The positive charge, as we'll see later, is 0 electrons, so it's the absence of electrons. And if for no charge to be there, we'd need a single electron species. So you can see that if that single electron is removed, it would be positive. If we add an electron, then it becomes negative. Alright, so that gives us what we need as far as figuring out how many electrons are in the pi system. Alright, so we've got 6 electrons in this pi system. And I'm going to put them in here. We'll put 1, 2, 3, and then 4, and then 5, and then 6. So you can see that we've clearly got an aromatic type situation going on here, because we have 6 pi electrons and everything's paired up. That's just going to be a consequence of it being aromatic anyway. So you'd say something like, this is just for this system over here, we have 4n plus 2 pi electrons, so it's aromatic. This one has 2, 4, and 0, so this would be 4 pi electrons. And this will be your classic anti-aromatic system. We'll have 1, 2, and then 3, and then 4. So we've got these 2 unpaired electrons. Very nasty situation. So this one here will be 4n pi electrons. So it's anti-aromatic. Now the other question it asks is, for any anti-aromatic compound, draw what it would look like if its geometry was planar. Well, we're assuming the geometry is planar, but due to the fact that you clearly see these 2 unpaired electrons, the actual structure will look like this. It doesn't matter which double bond we choose, but one of them needs to be broken apart so it appears as being 2 unpaired electrons. So this is what it would look like if it was flat. This really wouldn't exist in a flat state. If it did exist, it would exist in something that looked more like this. And I'll try and draw this in a 3-dimensional kind of situation. But it would probably try and bend out of the plane and put the positive charge up here. And if it did, then these could just bond as double bonds, because this wouldn't be subject to being anti-aromatic if it wasn't flat. It's only when it's flat that these 2 electrons have to be unbonded the way they are here. Alright, so that answers parts A, B, and C. There are 2 possibilities for part D that you need to be prepared for. First of all, which compound, A or B, is more acidic and why? Show a chemical reaction to support your case. Alright, so what you would do with this part D is it's asking about acidity. So acidity is about how many or how much H plus a compound will form when you dissolve it in water. Alright, so what happens is that something will take this H, usually a base, and that will leave H plus, and then some kind of anion. Alright, that's for that one. That's for A. Let's look at B. Now that's A, and I'll call this one A minus. Right, for B we'll do the same thing. And I'll call this one B minus. Right, so the first thing that we need to do when we're talking about comparing acidities is we need to draw diagrams that show H plus and whatever anion we get as well. The next step is to look at the anions and ask ourselves which one of those is more stable. Well, it turns out we already have information about this one. We already found out that it was aromatic. Now here's the hierarchy for stability for compounds that are aromatic or non-aromatic or anti-aromatic. We know that aromatic is going to be the most stable. We know that non-aromatic will be the next. And then the worst will be anti-aromatic. Now it turns out we know that this one's aromatic, and we know that this one is non-aromatic. Alright, so let's just say that. This one is aromatic. So it's more stable than this one, which equals non-aromatic. And we know this one's non-aromatic. It is cyclic, but it's not conjugated, so there's nowhere for this negative charge to go. But this one, being aromatic, means the negative charge is actually delocalized all around this ring, so that's what makes it more stable. Now the last thing we would do here is we would write some sort of statement, and that statement would be something like this. The statement would reflect the fact that since this anion is more stable, than this anion, it means that this compound, the original compound, is more acidic. Than that. So all three of these parts are necessary. We need to first of all show what the anions look like by drawing H plus in the anion. Next we need to figure out which of these two anions is more stable, and then we write a statement that basically says that since this anion is more stable than this anion, then this compound is more acidic than this compound. The rationale here is that if we're having H plus and an anion being formed, if you're getting a more stable anion, then you're also going to get a lot more of that anion and therefore a lot more H plus. So more anion equals more H plus. Less anion equals less H plus. So if we're getting less H plus, that means that it's less acidic. Hence the story with the statement here. This anion is more stable than this anion, therefore this compound is more acidic than this compound. Remember, the question was about these two compounds, these initial compounds, and we're using the stability of their anions to prove which one happens to be more stable than the other. Alright, so that's for the first part D, the one with the acidity. I'm going to erase all this now, and we'll go ahead and look at the alternate part D. Alright, so the alternate part D has an SN1 reaction. Now, let me remind you what an SN1 reaction is before I start this. An SN1 reaction is like this. Let's say you've got an alkyl halide, and usually it's going to be a tertiary system that we're talking about. And the SN1 has the bromine leaving first, and we form some kind of cation. This is a tertiary carbocation. And then some kind of nucleophile comes in and attacks the positive charge. And that gives us our compound. Alright, so that is a very typical SN1 process. What we know about the SN1 process, though, is that the slow step, or the rate determining step, is the first step. That is where the bromine leaves and puts a positive charge on the carbon that the bromine was originally attached to. So the same thing is going to happen over here as well. And we're only going to be interested in the first step, or the slow step, because that's what's going to indicate the speed, because we're talking about more easily, we're talking about faster. So we're only interested in the first step, and in each of those cases we will be removing the bromines and leaving a cation. It makes sense because up here we're interested in what the negative charges look like. Now this is a way that we can get positive charges onto these compounds. Alright, so let's look at that once I delete this. Alright, so our first step will be to take the original compounds. I won't worry about the hydrogen, just worry about the bromine. And we'll take the bromine away, and that will leave us with this cation and the Br negative. And we'll do the same thing to this compound as well. Take away the bromine, and that leaves us with this cation and Br negative. Alright, so now what we need to do is figure out which of these cations is more stable. Now we've already talked about the relationship between, we said that aromatic was more stable than non-aromatic, is more stable than anti-aromatic. And so we're looking here, we know that this one's anti-aromatic because we figured it out over here that it was anti-aromatic. So we know that this one is non-aromatic, so this one's going to be more stable. So this, which is non-aromatic, is more stable than this, which is anti-aromatic. And then what we can do is write a statement that links the stability of these cations to the speed of the SN1 reaction. So the one that's more stable, or forms more quickly, will lead to a faster SN1 reaction. So we can say that since this is more stable than this, then we can argue that this compound, whoops, with the Br on it, undergoes SN1 faster than this compound with the bromine on it. Now remember, the rationale of the last statement is that because this forms an unstable carbocation, it's not going to form that cation very quickly. Therefore, any SN1 reaction involving this compound would be very slow. This one would form the cation more quickly and would therefore undergo faster SN1 reactions.